So here's an example. Find the solution of the system x bar prime, or sorry, x prime, the derivative of this vector, and this matrix times the vector. So in order to find the solution, we first find the eigenvalues of the matrix, which is the determinant of 3 minus lambda and negative 1 minus lambda in those parts, and the 1 to negative 4 in the usual place. So that simplifies too. We got lambda squared plus 2 lambda minus 3, and then plus 4. So it's lambda squared minus 2 lambda plus 1 equals 0, or lambda plus 1 squared equals 0. And now, as you can see, we might have a problem, because if we don't get two linearly independent eigenvectors associated with lambda equals 1, we're going to have to do that thing I explained in the last video. So one eigenvalue we can find the usual way. Put in 1 here, we got 2, and put in 1 here, we got negative 2, and then row operations. Let's switch rows, and then negative 2 row 1 add to row 2, we get this, and that tells us that we're only going to get one eigenvalue, or eigenvector rather, that with k2 arbitrary, then k1 equals 2k2, because this says k1 minus 2k2 equals 0. So one eigenvector, and so it's just the eigenvector we get is the eigenvector 2, 1. Oh, I wish we could find 2, but we can only find 1. So that means, in order to get our solution, we need to find a vector p that satisfies this equation with, instead of 0 over here, the eigenvector that we found. And so we need to solve this system of equations, and same row operation, switch row 1 and 2, and then negative 2 times row 1 add to row 2, we wind up with this. For arbitrary, I'm going to call it P2, right? If P2 is arbitrary, then P1 is 2P2 plus 1. So the vector 2P2 plus 1 and P2, which is this, if you factored out the P2, and you could make this, which is really the same eigenvector as we got before, but then we have this new vector 1, 0 that we did not have before. So let's look at our two linearly independent solutions now. C1 times this one, that was kind of an obvious one. We got that eigenvector without a hitch. But we only got one, remember? So now also times e to the t, we have a second constant times t times our eigenvector that we found, actually two places we found that one, plus our extra vector 1, 0. And now, if you notice, if we do the Wronskian on that matrix, we'd have 2 e to the t here, we'd have 2t plus 1 e to the t here, we'd have e to the t here, and we'd have t e to the t here. I don't know why that's a y, it's supposed to be a t. Okay, got it. Fixed. So, let's see what that is. That's 2t e to the 2t minus 2t plus 1 times e to the 2t. And if you do the arithmetic on that, you wind up with negative e to the 2t, and that can never be 0. So there we have it, a second linearly independent solution.
Ooh, this is fun.
I hope so.